Hey Rampers! This video covers the second half of Chapter 5.1 in our textbook and relates the example that we used previously to some of the notation that we're going to be using as the rest of the semester continues. So you may remember in the previous video we talked about velocity and we tried to calculate the distance traveled by measuring velocity and multiplying it by the time interval that we think that velocity occurred. Well, as we did that, we then looked at the same data, but this time in graphic form. And we found that that multiplication we did was really just represented by the area of a triangle whose height was the value of the function and whose base was an interval of time. So it became clear that if we took more and more of these rectangles and made them thinner and thinner, we'd get a more accurate representation of the area under the curve. And so there became, hopefully we're going to stumble upon discovering the very interesting relationship between the area under the curve and a value that we're going to be able to use in calculus. So tonight we're going to introduce you to the notation that we're going to need. So please take good notes, pause often, and thanks for watching. In the last video we looked at velocity data that was measured over 2-second intervals, and we used that velocity data in order to figure out the distance traveled by a car over 10 seconds. So we took the velocity measured every 2 seconds. And if you look at that representation, that calculation, velocity times time equals distance, you'll notice that velocity is represented by the height from the x-axis or the time axis all the way to the curve, and the time is just the width of each one of these rectangles. So it became clear that if we calculated the area of each of these 5 rectangles and added them together, we would have an estimate of the distance, because each area is velocity times time. So that gave us really 2 means of estimating the area. We could use the velocity on the left-hand side of each one of these rectangles, or what they call each subinterval, and that would be known as a left-hand sum. Or we could go to the right hand, use the height at the right hand of each of these rectangles, and that would be known as the right-hand sum. Alright, now I want to take a look at each one of these in a little more detail so that you really are comfortable with this notation. We're not always going to talk about velocity. Sometimes we're going to want to generalize this to other different types of rates. Velocity, after all, is just the rate of change of our position in the world. But we may want to apply this to other things. So we're not just going to use velocity down at the bottom. We're going to take any length of time or any other independent variable, and we will call the beginning of our interval as t sub 0, or t naught as they say, and we'll stretch it all the way to our last measurement on the horizontal axis, and that will be t sub n. So there are n of these subdivisions. Each one of them is delta t units long, and each height is f of t. So if I want to look at the first rectangle here, I would, if I were calculating a left-hand sum, the area would be f of t at the left-hand endpoint of the first rectangle, so it would be t sub naught, times the base, and the base would be delta t. And then I would add the area of the second rectangle, whose height would be f of t sub 1. That is the height at the left-hand side of the second rectangle. Once again, its base would be delta t. And if I continued in that method, I'd get all the way to the last rectangle, and that would be the nth rectangle, and its area would be represented as f of t sub n minus 1. So it wouldn't be sub n because I need to use the left-hand height of the curve. So it's t sub n minus 1 times delta t. And that becomes what is known as our left-hand sum. Notice it goes, the first term is t sub 0, and it goes to t sub n minus 1. That's how you recognize a left-hand sum. Let's take a look at what the right-hand sum would look like. The right-hand sum is going to be calculated in a similar way. We will once again break up the total interval from t sub 0 all the way to t sub n into subintervals, but our height here is going to be not at t sub 0 but t sub 1. So I will write my first, my right-hand sum will equal f of t sub 1 times delta t plus f of t sub 2 times delta t all the way to f of t sub n times delta t. So since the last rectangle, its right endpoint has a height of f of t sub n, that becomes our final term. And so that becomes our right-hand sum. Okay, let's quickly review a little bit and compare the two. If I look at the left-hand sum, you'll see that I have each term is the area of a rectangle. So f of t sub naught times delta t plus f of t sub 1 times delta t plus dot 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 all the way into the last one, which is f of t sub n minus 1 times delta t. Now, if I look at the right-hand sum, you can see that, well, it's really similar, except that this time my first term is f of t sub 1, which was the second term for the left-hand sum. And that's going to be the case all the way through, that the left-hand sum has f of t sub naught in it, and the right-hand sum has f of t sub n. So the two sums are very similar, but off by a little bit. Okay, thanks for watching. I know this is a lot of notation and it's not really very well connected to anything at this point, but we're going to move on to some more concrete examples, and I think that will make this stuff gel for you a bit. All right, Ramblers, thanks for watching.